Hi there. In this lecture, I'll be talking about exploitation techniques. So far you've seen essentially one technique, but you should now at least understand very well how to apply that particular technique. So the ones that you've seen is a stack-based buffer overflow, which is a relatively easy one because you can find the return address to override easily. Other vulnerabilities are also reasonably easy to exploit, but they require slightly different techniques because you don't get the return address to override so easily. So you must find other ways. In this lecture, we will discuss a number of vulnerabilities and related exploitation techniques, just to basically make it possible to exploit more programs, and of course to learn how to protect against more cases. And what you will see is essentially that this is a puzzle, but it can generally be solved. So you can make it harder for the attacker, but it's very difficult to make it impossible. So, some vulnerabilities can be used to create a buffer overflow. You've seen buffer overflows. For example, integer overflows can often be used to bypass length checks and create a buffer overflow. Others provide an arbitrary write, so they enable you to write a value of your choice at a location of your choice. So this could be used, for example, to override a code pointer, which brings you back to the spot where you were with the overwritten return address. So an example would be a buffer overflow on the heap or a format string. We will be discussing these vulnerabilities. Next, some vulnerabilities might only allow you to corrupt specific data. So essentially, based on the bug in the program, you can only override a particular variable or perhaps even a part of a variable. Well, what can you do with these? There's still all sorts of ways to exploit these. For example, override the pointer to create an arbitrary write, or create a buffer overflow by overwriting a length of an index. Or you could make this an authorization violation by changing a path. There are many ways in which this can be abused, and examples where you need these kind of techniques include use after free and type confusion. Finally, going from vulnerability to code execution is often a puzzle, and you must essentially chain many steps together. So basically, in this lecture, we will be discussing the steps that you can take to get closer to your goal of exploiting the target program. Now this goes even stronger if defenses are applied. So in a later lecture, we will discuss defenses that make these attacks harder. And then you have to apply even more techniques to also get around the defenses. So, an overview here of the different techniques that we will be discussing in this lecture. So in this particular video, I'll only consider the first one. The other ones will come later in separate videos. So the first one is buffer overflows, and in particular different types of vulnerabilities for buffer overflows. There are many different types of buffer overflows, and it's a very common vulnerability. In a later video, we will discuss also different ways to exploit it, depending on where the buffer overflow actually is. Next, we'll be discussing integer overflows, format strings, use after free, uninitialized variables, and type confusion. Now, all of these are well-known classes of vulnerabilities that are fairly common in the real world and that are often exploited. So it's important for you as a security expert to understand how to exploit them. Also, for the assignment, you're going to need to become a hacker and exploit vulnerabilities like these. Finally, we'll discuss some of the tools that you may be able to use to help you perform such attacks. This is the first part of the exploitation techniques lecture on buffer overflows, namely the different vulnerability variants. So how do buffer overflow differ in ways that are relevant for the exploitation techniques that we'll use? We'll go over some variants and discuss exploitation techniques to abuse these particular variants. And you'll see that in the end, you're often using similar tricks. So you basically need to start understanding what kind of approaches there are available and then see how you can combine them to perform a real attack. So in general, buffer overflows are among the most common mistakes in C and C++. They are very widely exploited, and there are many vulnerabilities out there that are based on buffer overflow type vulnerabilities. So it's also among the most popular attacks, and this is all in part because it's also very versatile. So you can use buffer overflows both locally and remotely. So in simple attacks, we saw often that you needed a lot of control over the program to be able to abuse them. This is not the case for buffer overflows. Buffer overflows, you only need to insert the data that will overflow the buffer, which often includes length fields or just an arbitrary amount of data. Moreover, buffer overflows are often used to change the control flow, as we've seen in the stack-based buffer overflow example, but can also often be used to modify data, which can also be useful in itself. Well, these attacks are often dependent on the architecture and operating system version, so do keep in mind that if you see just a C program, you may not know ahead of time whether the vulnerability, the buffer overflow vulnerability in there is actually exploitable. So the vulnerability is always there if there's a possibility to go over the end of a buffer, but it doesn't need to mean that it's exploitable in every circumstance. And moreover, in some cases, the exploit might be different than in others. So you need to really analyze the assembly code to see what is happening. This is a very important step in exploiting a buffer overflow effectively without a lot of brute forcing. So there's also a lot of research into finding, automatically exploiting, and hardening against buffer overflows. So if you're going to look at research, this is basically the first problem that you tackle, because it's a relatively easy one. And this is also exactly the reason why I start off this lecture with buffer overflows. It's a relatively simple case, but still very important and widespread. So the example that we showed had some particular properties. For example, the example that we've seen before was a contiguous buffer overflow. That is, you have to override everything from the start of the buffer to the location where your target is, to the location where the thing that you wanted to override is, so typically the return address. It's also possible to have buffer overflows that are not contiguous, which means that you can skip some of the place in between and have a more targeted primitive that only overrides that thing that you want to change. Moreover, this buffer overflow had arbitrary length, so you were able to put as much data in there as you want as an attacker. Now, in many cases, buffer overflow vulnerabilities are constrained in the sense that you can only insert a limited amount of data, and you still have to find an effective attack in this case. Another is that this particular overflow was null terminated, which for example meant that our shellcode could not use null values. So in other cases there might be other restrictions, or perhaps even none at all. So for example, it's also common to have a situation where you specify a size field, and then the amount of data read is based on the size field rather than whether there's a null byte there. This changes somewhat how you would exploit the vulnerability. It means that you can now inject null bytes if you want to, but it also means you have to find some way to bypass the fact that this size is often checked. Finally, this buffer overflow was stack-based. So we had a buffer on the stack that we overflowed into the return address, which is a relatively simple case. We will also discuss other cases here, such as overflowing a buffer on the heap. Now, along all these dimensions, variation is possible, and we will see some variation in these lectures. If you want to attack a program, the first step is to find the actual vulnerabilities. So in case of buffer overflows, let's think a little bit about how you would recognize a buffer overflow. Do note that this is also important, not just if you want to attack the program, but also if you want to write a program without buffer overflows. So these cases are telltale signs of possible buffer overflows. One of them is fixed size buffers. Especially on the stack, this is common, and it means that you need to explicitly check whether whatever you're writing fits in the buffer. So there might be incorrect assumptions and there might be missing checks. Passing a pointer to a buffer without a size is also often a sign of buffer overflows. If you do this, it means that the function you're calling cannot check whether it's going to read or write within the bounds of the buffer. Which also means that if you pass something without knowing how much it's going to write, then there could be a buffer overflow. So check function signatures to see whether there's a risk like this. So a typical example is the string copy function that we've already seen. String copy does not get information about the size of the destination buffer, so it cannot check. And we must check when we call it to make sure that we're not going to write more data than fits in the buffer. Another typical one is an array access without a size check. So say an array index within a loop is typically pretty safe because the bounds are encoded in the loop. There could be some cases where something changes and this doesn't work, but in a general case that is fairly safe. But if we access an arbitrary element, especially if the index is somehow derived from user input, then we would expect an explicit check. If there is no such check, it's quite possible that there is a buffer overflow there. And finally, if you use pointer arithmetic. Now pointer arithmetic is very nice in C and C++. It's super efficient and it allows you to write some code that can do really low-level manipulations without writing a lot of code for it. So pointer arithmetic is nice. But it's also one of those places where it's very easy to make mistakes. And in particular, if we do pointer arithmetic, we might also forget about the bounds of whatever we're writing to. So what you would hope to see for correct code is that there is some size or end pointer pointing to the end of the buffer that allows you to check while writing to the buffer. If there is no such thing, again, it's a sign that there might very well be a buffer overflow there. Now these approaches are not foolproof. So first of all, it's quite possible that we have cases that do not match and are still vulnerable. So for example, if there is a dynamic allocation, we might still have a buffer overflow if the allocation size is computed incorrectly in some cases. Likewise, even if there is a check, there's a good chance that the check might be incorrect. And we will actually see cases of these in the examples of buffer overflows that are discussed in this lecture. However, it's also possible the other way around. Perhaps it really looks like a buffer overflow, but in practice you cannot exploit it. So a typical case for that is if the check has already been done previously. So it is actually good practice when you're getting data from a potential attacker, so from a user, to check as soon as possible whether the data makes some sense. If you sanitize the data like this, it's quite possible that a vulnerability later on is not actually exploitable because the inputs that were risky were already taken out. I just discussed a number of signs that there might be a buffer overflow. Some other signs are specific functions that are known to cause vulnerabilities in programs. These actually match the scenario I already mentioned, namely cases where you pass a buffer, pointing to a buffer, without specifying the size. However, since these functions are in the standard C library, they're very widely used, and it's very likely that you will encounter vulnerabilities including them. So the first, getS, is particularly bad. So this function is so bad that the compiler will warn you when you're trying to use it. So this function is impossible to make secure pretty much, because it reads data from the standard input and continues reading up to the point where there is a new line. So based on the input, you can always overflow a buffer because you can provide as much data as you want. Right? So this is completely unsafe, should never be used, but there's an alternative, fgetS, which does specify the size of the buffer. String copy and string cat we've already seen. So string copy will copy as much data as there is in the source without considering the size of the destination because it doesn't know how large it is. String cat is similar and is even more confusing potentially because it concatenates strings. So whether something fits in the destination buffer also depends on how much stuff there already is in the destination buffer. This means you need to be very careful to do a good check if you want to use these functions. A better option is to replace them. So there are also alternatives that do take a size argument and that will check to make sure that they don't go out of bounds in the buffer. So these are, for example, string ncopy and string ncat, which are somewhat safer if you specify the size correctly. But we'll get to some issues with string ncopy as well later. Then we have sprintf and friends. So there's a bunch of functions that format strings. Now these functions have an output length that depends on the format arguments. So if there's a %s format, for example, it's replaced by a string that's specified as an argument. Now if we assume that this string comes from a potential attacker, then they can specify a string that's as long as they want, which makes the final string also as long as they want, which overrides data. So in this case, again, we need to use a better form of the function. String nprintf will actually write only the specified number of bytes to the buffer. So this is much safer. Then we also have scanf and friends, which are used for parsing, and they can parse strings and store them into a buffer. So in this case, the length depends on the input string. And if the input string is attacker supplied, which is actually very common in scanf, then it means it can write an arbitrary amount of data to your buffer, which you obviously do not want. So in this case, you have to make sure that you put a bound on any %s formats there are, because %s in itself is any length of string. So it can take any length, and there's no buffer that can fit this. You need to put an explicit bound to make sure that it doesn't exceed the available space. Then also, your own input functions are a major risk. You always need to check your assumptions and make sure that you're not going to go over the end of the buffer for whatever reason. So while you're writing into a buffer based on some input, always be sure to check. Here we have a very simple example of a different class of buffer overflow attacks than what we've seen so far. This is an array overflow. It should be fairly obvious, I think, what is happening here and why this code is vulnerable. So we have input from the user, which are the arguments. These arguments are parsed into integers. And then what we do is we assign elements of the array, or one element of the array, at the index specified by the attacker with the value specified by the attacker. When we do this, we do not check the index, so the attacker can specify any index. Now, when accessing an array element like this, we compute the address, and by specifying the index, we can make the computation result into any address. So we can find a nice address, for example, to write the return pointer to, specify the index corresponding with that, and then we can also specify the value that is to be written there. This is a very obvious case of an arbitrary write vulnerability. So this vulnerability provides an arbitrary write primitive that we can later use to hijack control or corrupt data. So let's analyze this code now. Let's see if we can understand the assembly code and use that to understand how to attack this very simple program. Now we start off, as always, by setting up the stack frame. That is fairly obvious. Next, we allocate space for the local variables. We've also seen that before. Then we store the arguments, and then here it starts getting interesting. We start loading the data from the user. So here we load minus hexadecimal 60 RBP into REX. So this was the arguments, right? So here we're loading argv into REX, and we're adding 8, which means we're taking element number 1, because each element is 8 bytes, and we dereference it. So at that point, we have argv1, which is attacker controlled data. So that is more or less by definition interesting. Now, the value of REX gets passed here into RDI, right? So RDI is passed to string toll, because RDI is the first parameter, So here we can indeed identify that the index ends up being parsed and see where it is stored. And the index ends up being stored here. So, here. So Rx ends up at RBP plus 8, which is the location of the index variable. Well, this knowledge we can use to recognize the later code, because we know this is now an attacker-controlled value. So let's look ahead, and eventually we find this interesting instruction. Okay, so this instruction is clearly an array reference. We have here RBP plus 0x50 plus REX times 8. Well, that is very obviously an array index. REX is very obviously an array index here. And the element size is obviously 8 bytes. So then 0x50 RBP is the start. And we can also link this back again to the index, which is shown on this line. So we load the index that we just parsed into REX, and then we use REX into an array reference. Well, here clearly there is a potential for an attack. Well, what do we need to know here? Well, especially this information. We traced back the index to the user's input, and we found that it's used to index the array at this address. Now we can use this address to compute what the index should be to get the results that we want. Now let's figure out what the index of the return address is. So of course the array has only 8 elements, but after these elements there's more stuff in memory, amongst others the return address. So let's see, if we assume the array just continues forever, which it effectively does because there's no bounds check, which index does the return address end up? Now the array, as I just showed you, is at RBP minus hexadecimal 50, also known as 80 in decimal. The return address is at RBP plus 8. Now this is because it is pushed right before the frame pointer. Right, so the return address is pushed when we call the function, and then the first thing the function calls is the frame pointer. And then the frame pointer is going to point to that RSP, which means the thing pushed just before it will be at the next higher address on the stack, which is RBP plus 8. Note that this is always the same without optimizations. However, it might not be as easy if optimizations are enabled, because then RBP can be used for different purposes. So, we know now where the return address is, and we know where the buffer starts. So to compute the index, we need to compute the difference. We need to go over this difference by using the index. So we simply subtract the two from each other. So the return address is the higher address, the start of the buffer is the lower address. And we see if we subtract them, the RBP cancels out. Now this is part of what makes it so easy to attack vulnerabilities on the stack. Right? Everything is relative to each other. Everything contains the RBP. So if you compute a difference like this, the RBP simply cancels out. In this case, the result is 88 in decimal. So this is the number of bytes that we would need to write starting from the start of the array to come to the return address. Now, the index then is the offset divided by the element size. So the index that we need to go to get to the return address is 11. Now, we know where we can overwrite the return address. So as before, the next question is what to override it with. Now let's just do the same thing as before. Let's load the shellcode into the environment. So we specify an environment variable containing the shellcode. Now remember the formula that we saw before. We start from the bottom of the stack, and then we basically subtract what is there before this to end up at the start of the shellcode. Now this formula we can use again. If we assume the program is called /array overflow, then we can compute the number. So keep in mind that the program name matters because its length is a factor here. If the program name is longer, the shellcode environment variable ends up in a different place. So we do need to know this, but knowing this, we can compute exactly what the address will be. Now, let's put that together and make it into an exploit. First, we disable ASLR, which is address space layout randomization. We'll discuss this in more detail later, but it ensures that you cannot just use pointers, because the pointers will be randomized. You need to figure out which pointer belongs where. Next, we compile the shellcode. So we have it in an assembly file. We want to generate an object file. Now from this object file, we strip only the code using the object copy command. Now we have a binary file that contains only the shellcode binary instructions. Next, we use env-i again. Env-i replaces the environment with what we specify here, and what we specify is that the shellcode is supposed to be whatever is stored in the shellcode.bin file that we just created. And then the real exploit is specifying the right arguments to array overflow. The first argument is the index and the second is the value. Index is 11 as we have computed, and the value is the location of the shellcode, which we have also computed. If we do this, we get a shell from the program. So the attack was successful. Now take a look at this nice little program. Even though we do string copy here, which is of course an unsafe function, we nicely perform checks to make sure that the strings fit in the buffer. So the user specifies two strings, argv1 and argv2, which are copied respectively into the host and the path. Both of these variables fit only 48 characters, but we nicely make sure that this fits. So this is a nicely secured program, right? There should be no vulnerability here because we properly check. Well, turns out this is wrong. We forgot about the null terminator. So if argv1 has a string length of 48, it means that there's 48 characters as well as a null terminator. Now the 48 characters fit, but the null terminator does not fit. What happens? We already know. The null terminator will overflow into the next buffer. Is this an issue? Well, we will see why this is an issue, and in fact this is a very common issue, because it's easy to make a mistake in performing the check. So in this case, making a check greater than or equals to would have prevented the issue. The example on the previous slide is an example of a very common class of vulnerabilities. So unlike cases before where we could overflow a buffer by an arbitrary amount, off by 1 errors make it possible to only overflow an array by one element. Well, one element could be 1 byte, as in the previous example, or 1 integer or a longer thing, but the amount we can overflow is limited, which changes the techniques you use. However, these overflows are very common because it's basically a matter of confusing the comparison operator. For example, either less than or less than equal to, greater than or greater than equal to, and also forgetting about the string terminator. So in this particular case, it's actually both. However, there's also other cases possible. For example, in a loop condition, you might use the wrong comparison and you will also get an off by 1 overflow. So, similar to regular overflows, but more limited. These overflows can modify, in some cases, the least significant byte of a pointer or index. This is because, as we know, Intel is little endian. So, exploiting a vulnerability like this is all about understanding how corrupting this single byte can be used to perform an effective exploit. To give some idea of how to exploit an off by 1 vulnerability, let's work out the example and see how we can get to an effective exploit. This slide shows the assembly code for the program. Now I imagine you may not remember all the details of the C program code, but there's very little that actually matters. So what matters in this case is that the things we're looking for, the buffers we want to find, are arguments to functions. So the host buffer was an argument to the first string copy, where it takes the value of the parameter supplied by the user, which might be the attacker. Path is the first argument to the second string copy, where it also takes the value of a parameter specified by the attacker. And then finally, URL is the first parameter of sprintf, because we're formatting a URL into a buffer, into the URL buffer. So keep in mind that because of the limitation set for the host and the path, the URL should not become too long. But let's take a look what can happen here. So first of all, now we're looking for the locations of the different buffers. How can we do this? So let us trace back how the buffer values get to the calls. As I mentioned, host is the first argument to string copy. And as you may remember, the first argument is passed in RDI. So we want to know the value of RDI on this line. Now, this is easy because it's actually assigned on the line before based on REX. So let's look back what the value of REX is. The value of REX is loaded by the lia instruction. Now this is a good indication that we have a pointer to a buffer being loaded. So now we know that this is the location in the stack frame where the host buffer is stored. Now we can do the same for the path, and in this case we find very easily that here we have RBP minus hexadecimal A0. So then finally sprintf is again very easy. We have sprintf here, and we want to have RDI, and we need the value from REX, which is again loaded with a lia instruction. So now we have the locations of all the parameters, and we can figure out what the layout of the stack frame is. Why is this important? Because this allows us to see what the single byte that we can overflow can actually achieve. So let's do that. Right here we have the variables that we derived. This is what we found out so far. We now know the location of the buffers, and we also know how much we can write into them. So the host and path buffers, we can both write 48 characters of actual content and then followed by null byte. The URL, so you may have to look back at the code a bit, but it turns out that you can write the number specified here. 8, which is a fixed string, plus the host length, plus the path length, plus a null byte. So essentially it concatenates the two with some extra filling added to it, which is the 8 extra bytes. And then finally, the return address, like before, is at RBP plus 8. Now what can we do with this information? Let's compute the distances between the buffers. So host and path are next to each other, and they are directly next to each other because the host buffer and the path buffer are both 48 bytes, and the difference between their addresses is also 48 bytes. So host is at the lower address, so if we keep writing to host, eventually we end up in path. So the final byte that we are overflowing is stored in path. Now from path to URL is also 48 bytes, which means that we can also overflow 1 byte into URL. And from URL to the return address is 120 bytes, which means that if we want to perform an attack, we should write 120 bytes followed by the return address. So this is what we can derive from the assembly code about the stack frame. Now let's think for a bit. We were first copying the user argument into the host buffer, and then the user argument into the path buffer. We overflowed 1 null byte from host into path. This means that we're actually not overflowing any relevant data, because path is only initialized later. However, this time it goes the other way around. When we write into path, we delete the null byte, which is overwritten by the path. So let us think how this could affect the exploit. How to exploit this vulnerability? Well, we now have all the important information. So what can we do to get to the return address? Well, first we pick a host of exactly 48 characters. This is the only way that we can abuse this particular off-by-one vulnerability, because if we have less, we don't have an overflow, and if we have more, the check will stop us and not actually perform any useful work. So host must be exactly 48 characters, and then it overflows the null byte into the first byte of path. Now, next, the string copy of path overrides the null byte. So the null byte was there, terminating host, but it's now gone. Host is no longer terminated. So what happens when we read host as a string? Well, it turns out it will simply look for the next null terminator, which is at the end of path. This means that the length of host as stored in memory until the null terminator is now 48 characters that we wrote, plus all the characters for path. Well, now host is quite a bit longer, potentially, than what was expected in the check. So this means that when we get to sprintf, it no longer fits necessarily in the URL buffer. So the length that we get is 8, which was the fixed part of the string, plus 48, which is the full host buffer, plus 2 times string length of path. Because the string length of path is added when path itself is copied, but it's also added after the host. So we now know, if we know how far to overflow before to get to the return address, we can fix the, we can attack this by simply computing the right number. So on the previous slide we already saw this. So what we now basically need to do is plug in the number of bytes that we want in the formula and then just solve the formula. Unfortunately, it's not actually that easy. There is something else that we need to consider, and it has to do with pointer storage. So how is a pointer stored? Well, actually a pointer is stored just like an integer, and it just stores a memory address. So it is an integer containing a number that specifies which location in virtual memory to use. Okay, so far so good. The 64-bit Intel architecture stores pointers as 64-bit integers, because it's after all a 64-bit architecture. However, it turns out that it only uses the 48 least significant bits. So basically, there is the assumption that you don't need more memory, whether physical or virtual, by the way, more memory than 2 to the power 48. So the other bits are not implemented, not used, and must be 0. If you have a pointer where these bits are set, except for the special case where you have some kernel pointers, but if you have a user pointer where these bits are set, it's always an invalid pointer, and it cannot help you perform the attack. This means every pointer contains 2 null bytes. So there are 16 unused bits. The most significant bits are always null. Well, this is an issue with an attack like this, because we were doing a string write. Now another consideration. I mentioned this on the lecture on assembly. Integers are stored little endian. This means that the little end, the least significant byte, is stored first, at the lowest address, whereas the most significant byte, the big end, is stored last. Let us combine these two things. What does this mean for the attack? Well, it means that every pointer has 2 bytes that are null. It also means that these bytes, which are the most significant byte, are stored at the highest address. That is, at the end, if you consider it from an overflow perspective. So every pointer ends with 2 null bytes. Now we can compute the input length. We now know that we need to write 6 bytes to the return address, which are the actual bytes of the pointer. The other 2 bytes we should not write, because we cannot write null bytes. Only 1 null byte will be added at the end. However, since there's already a valid pointer in the return address, we don't need to write the null bytes. So we only write the 6 bytes that actually matter, and the null bytes are already there. Now, we know the length of the URL, and we know the distance from the URL to the return address. So now, as I promised, we can simply solve the equation. The required input length is obtained by saying that 120, which is the distance from the URL to the return address, plus 6, which is the number of bytes we need to write into the return address, is equal to the total length of the URL. So we can simplify this equation by combining the terms that do not involve path, and then we divide those sides by 2. It turns out that to get the exact right exploit, we need to set the string length of path to 35. So if we have 35 bytes, the URL becomes long enough to overwrite exactly the return address without harming the null bytes that are there. So to wrap this up, how do we actually perform the attack then? Well, we run the vulnerable program. In the environment, we inject shellcode, just like before. The first parameter is 48 characters, which must all be non-zero, because otherwise the string would be terminated, but they may otherwise be garbage. These characters do not actually matter for the attack. And then the second parameter path must have 35 characters. The first 29 are non-zero garbage characters again, and the final 6 are non-zero bytes of the pointer to the shellcode. So this pointer will be written twice, but the first one will be ignored. Only the one that ends up exactly over the return address will be used. And the program will jump to this pointer to the shellcode. And then we complete the attack. So this is what it looks like when we actually perform it. We compile the program. As before, we need to disable some of the defenses. So the stack protector would prevent this attack. And we need an executable stack to be able to run the shellcode. And then we also disable ASLR, because ASLR would make it hard to predict the location of the shellcode. So now what we do, we compile the shellcode into an object file, and then we extract the machine code from the object file into a file called shellcode.bin. And now we can very easily just launch the program from the command line, specifying the arguments that will break it. So env-i, this is important because we replace the environment to have predictable numbers. We insert the shellcode that was just inserted using, that was just created using the object copy utility. We run the program with the two parameters. The first parameter is simply 48A characters, and the second one we specify the return address. So this return address was computed exactly as before. So you need to take care to consider the length of the program name, which influences the value of the return address. But if you do this, then you can easily find the right value and plug it in here. So now we created a string, an exploit, that can exploit this program. So there's a small warning here. So because the shellcode contains a terminating null byte at the end, Bash will actually see this null byte and will realize that it's unable to insert this into the argument. This is not an issue because this null byte was there to terminate the shellcode anyway. So it doesn't matter. We can ignore this warning. And now we see exactly what we expected. We have a very long URL, and this URL contains all the garbage and contains the return address twice. So the first one has a lot more garbage because it is actually host plus path. And then after the slash, we have path again. Well, the garbage that we see here as the weird blocks, that is actually the return address, which of course is not printable because they are not ASCII characters. Well, this works. We actually get a shell from this that we could use to exploit if the program were actually set UID. Now let's get rid of the off by one vulnerability. So we let libc do the check. The string and copy function makes sure that we never copy more than the size of the buffer. So this should finally be secure, right? We now make sure that the username and password buffer are never overflown. Well, actually there is still an issue. Even though string and copy never copies more than 512 bytes, this is not necessarily a good thing. Because some functions, such as string copy, limit the amount of data but do not include the null terminator if they are clipping the string at the end. So if we have more than 512 characters, or actually if we have 512 characters or more, string and copy not only chops off the rest of the string, but it also removes the null terminator if it doesn't fit within the limit. So this means that as before, in the off by one case, the string includes the adjacent buffer due to a non-terminated string. Again, we might copy too much data, and we get into exactly the same situation that we were in the previous case with the off by one vulnerability. Now this is how to perform the attack. Here we see first the compilation again, disabling ASLR, compiling the shellcode, everything that we've already seen. Now, in this case, again, we did the computation. You should be able to do it yourself now because you know all the important factors. And then we inject 512 characters in the first buffer. So again, we fit exactly the right number of characters in the buffer, which means that the null terminator is not written. And then the buffers are combined. Just like in the off by one case, for the second buffer, we write some data followed by a return address. And again, we can see that this leads to a successful exploit, yielding a shell. One final remark about buffer overflows. So the buffer overflows that we've seen so far cause data corruption by writing data out of bounds. However, this is not the only case that is actually important. In fact, buffer overreads, where there is a read outside the bounds of some buffer, are also a major problem. And in fact, they can be just as harmful, because a read might be able to, for example, leak sensitive information. Think about passwords, crypto keys, personal data, and so on. Moreover, during the defenses, we will discuss ASLR, address space layout randomization, which requires pointers to be hidden. Well, it's very, very likely that any out-of-bounds read will be able to leak a pointer, which breaks the ASLR defense. Moreover, there are plenty of important vulnerabilities. Especially the heartbleed vulnerability is a very well-known case of a buffer overread vulnerability causing serious damage, because this vulnerability allowed an attacker to read crypto keys from web servers in the OpenSSL library, which means that many web servers were vulnerable for a long time, and we simply do not even know what was leaked. Many passwords of users may have been leaked because the crypto keys were exposed, and we will never even find out.